Last time we have studying the change of basis for flat space indices, which means that we are changing the basis for the tangent space, but actually we always work with differential forms instead of vectors, so we are working on the cotangent space, but that's the same. They are dual to each other, so it's basically the same. The change of basis is completely generic, and we will later make it more specific, but in this moment it is totally general. So we were considering the transformation of the spin connection, and we got this formula here, which is almost the end, what we want. In particular, observe here that this object is just the spin connection, because EC is contracted with this index. So the first part, reordering a little bit the indices, is omega AF. We first write this one. Small omega FE, big omega to the minus 1 EB. And then the second term is made of a differential form of a vector. Actually, this is a vector acting on a function and some other things. So let me order the indices here as well. Big omega AE. Then we have EC omega to the minus 1 EB. What is this EC of, let's say, a function f? E superscript c is a form. These are forms. And E subscript c are vectors, derivations. And we know that when there is a contraction of indices like this, we have a Filbang and the inverse Filbang, so the result is the identity matrix, delta mu nu, and the contraction dx mu partial over partial x mu f is just the differential of f. So this is very, very simple. So this thing is just like saying the differential of the function in parentheses. And then we can condense the entire result in a very simple matrix formula, because we can understand the indices. So we have omega prime. Then we read the indices. You see big omega AF, small omega FE, big omega to the minus 1 EB. That's like saying in matrix notation omega, small omega, big omega to the minus 1. And the last part is omega AE D omega to the minus 1 EB. So that is omega D omega to the minus 1. That is the formula for the transformation of a connection under an arbitrary change of basis. And using this, we can transform everything we want now, because we know how the field bind transforms. So actually, the differential forms, because we always prefer to work with them. And so in matrix notation, we can write it this way. So for example, if you want to transform the torsion, what do? To transform, let's write the definition of torsion. Torsion is the covariant derivative of the field bind of the differential form E. So it's the exterior derivative plus the spin connection wedge E. And so T prime, we could write it del prime E prime, but what is it? We just replace primes everywhere. There is no prime in the differential because there is no change of basis that concerns D, has no indices A or B. But there is a prime on E and there is a prime on omega. So let's replace. So you have D of omega E plus omega prime, which is big omega, small omega, big omega to the minus 1, plus big omega D, big omega to the minus 1, and then times E prime, which is omega E. Then we apply the rules of the exterior derivative of a function times a form. That's the differential of the function wedge, the form, plus the Leibniz rule here applies with no minus sign because you have to cross a form, a zero form. And so you have omega dE. The other terms are simpler because here you see you have capital omega, small omega, capital omega to the minus 1 times omega gives 1. So you just have this. And the last term is big omega d omega to the minus 1 omega E. Omega, yes. Now, let's check these two terms first. These two terms can be written as omega del E. Omega times the torsion, and the other two cancel out. Why? Because you have to remember that 1 is equal to omega to the minus 1, and so d1 is 0. If you take the exterior derivative, that's d omega to the minus 1 plus omega times d omega to the minus 1, which means that multiplying by omega to the left, 0 is equal to d omega plus omega d omega minus 1 omega. So this and this are opposite to each other and they cancel out. So you see that this, the torsion, the covariant derivative transforms correctly as expected because the change of basis gets out and the torsion transforms as a vector, same way as E prime does. So the transformation of E prime and T are the same. We can repeat this for the curvature R, that's a 2 form, and we recall that this is its definition. So if you want its transformed version, you have to calculate this object. Omega prime, we just replace it with what it is. So you have d capital omega small omega capital omega to the minus 1 plus capital omega d capital omega to the minus 1. And then you multiply these transformed spin connections twice. So you have omega, small omega, capital omega, plus capital omega d capital omega to the minus 1. And then you have to work out the exterior derivative of these two and do everything you need. So let's do it. Here we have d omega, d capital omega, small omega, omega to the minus 1, plus capital omega, d small omega, omega to the minus 1, minus, because now when dx on omega, capital omega to the minus 1 has to cross a 1 form and a 0 form, so a 1 form in total, so there is a minus sign. And then you have d omega, d capital omega to the minus 1. D does not need to act on d omega minus 1 because d squared is 0. In the second line, you have just to multiply. Recall that omega to the minus 1 times omega is 1. This simplifies things a little bit. So the first is omega, omega, capital omega to the minus 1. If you multiply these two, you have plus omega, d omega to the minus 1, omega, small omega, omega to the minus 1, plus now this times that, big omega, small omega, big omega to the minus 1 times omega. So we get this. And the last one, which is omega d capital omega to the minus 1, omega d capital omega to the minus 1. Something simplifies. For example, this object and this object are opposite to each other, but there are other things that simplify, because check, for example, this and this one, they factor a d omega to the minus 1 to the right, but what you have in front are opposite to each other for what we proved earlier. So those two things cancel out as well. And similarly, these two things cancel out for the same reason. They factor small omega, big omega to the minus 1 to the right, and what multiplies them is again two opposite things. So those cancel out as well. We just remain of these two terms, which have one omega to the left, one omega to the minus 1 to the right, and in the middle they have just r. So what you get is omega d small omega plus small omega, capital omega to the minus 1, and this is omega r omega to the minus 1. Which tells you that, again, the curvature transforms correctly because the upper indices get an omega to the left and the lower indices get an omega to the minus 1 to the right. Another thing that we can write is from the torsion, which we saw previously, and the transformation of the field by, and the transformation of the torsion itself. We can write it like this, nabla E. We can write omega to the minus 1 E prime equal E. So this is omega prime del omega, not omega prime, omega del omega to the minus 1 E prime. Yes. So since the torsion T prime can be written like that as del prime E prime, you can, if you want, say that the covariant derivative transforms like this. If you want a formula for the transformation of the covariant derivative, that is it. So let's see some applications of this, which are quite important, because let me stress that what we have been studying here is a generic change of basis. Consider, for example, the relation between the field by and the metric. And consider a generic change of basis. Is it G mu nu prime equal to E mu A prime eta AB E nu B prime? In general, no, because EA are the vectors that E subscript A diagonalize and orthonormalize it with a signature the metric. But this relation, which we have never used indeed so far, does not survive a generic change of basis. If you want to have that relation after the change of basis, you cannot use a generic linear transformation omega. You have to use a special linear transformation, which is the one that preserves the metric eta AB, which is a Lorentz transformation. So let's see, G mu nu prime would be equal to what? Omega A B E B mu and eta, well, it's better to change the name of the indices here, A B omega B D E D nu. Now, yes, so the question is, since we are just changing the basis, and the basis is the basis of the tangent space, so the flat space indices, it shouldn't concern the space-time indices, and the metric shouldn't know, is it true that the metric is invariant? Well, the metric is invariant, you see, only if which is an if and only if this product here is again eta CD. So that is a Lorentz transformation. So omega AC eta AB omega BD, that should be equal to eta CD. But that is a Lorentz transformation. So a change of basis that preserves the flat space metric everywhere is called a local Lorentz transformation. And for that, we will use lambda instead of omega. And let me emphasize that it is a local Lorentz transformation because precisely like omega, it can depend on x, but it is not a matrix of the general linear group. Remember, this is a generic, but it's a Lorentz transformation for every point x. So Lorentz transformation. Which means that everywhere, for every x, you must have this identity. The identity we saw before. So lambda AC eta CD lambda dB. For every x, everywhere. So we have two types of transformations, those that preserve this diagonalization. So in the new basis, the new forms EA prime still diagonalize the matrix, the metric, yes. And those who don't, because again, everything we said so far did not need the diagonalization. Indeed, we never talked about eta AB. So we can change basis in every way we like. And for example, if our E is the one that satisfies this relation, the new one will not. And that means that we will have what? Let's see some explicit examples, so that gives us an idea. What we can do with a generic change of basis. A more general, so not a Lorentz transformation, a more general change of basis. Well, for example, let me recall that EA is, these are forms, is something like that. This is a change of basis. Imagine this as the EA, this is the omega, and this is the EA prime. This is the change of basis that takes you from the space-time indices mu to the flat space indices. And every formula we derived can be used now with this kind of omega to connect every formula we get in space-time indices with formulas we get in flat space indices. This is a change of basis, because dx mu are the differentials in the basis, canonical basis of coordinates, and these are the differentials in the other bases. Of course, this is a transformation that's not a Lorentz transformation, and certainly it does not leave the metric diagonalized. Indeed, the metric becomes g mu nu of x. So it changes. How can we use this? So for example, we can work out the transformation of the connection. In the basis x mu, we have defined the connection as the Christoffel symbols. In the other basis, we had those objects that allowed us to define the spin connection. So let me do some trick here. These objects define the spin connection. If we do the same here, we should do something like this. And we can define the analog of the spin connection as a one form for the Christoffel symbols, taking the symbols and contracting the first lower index with the differentials of the basis of the cotangent space with that choice of basis, which is dx rho. Then the formulas we found for the change of basis allow us to connect the Christoffel symbols and the spin connection, because in one basis you have the Christoffel symbols, so we just apply this formula, and you will have in the transform basis you have the spin connection, in the starting basis you have the Christoffel symbols. So just apply that. What happens? So we just replace. Here we find the spin connection. Here we find the Christoffel symbol, and omega is the feedback. So this is some, let me say, now we arrange the indices. So this is a little bit too fast, but when we write the first one with the indices, it's easier. So here it is omega AB, this is E, this is gamma, mu, nu, A, mu, e to the minus 1, but e to the minus 1, we don't need to write minus 1 because when the spacetime index is raised, it is minus 1. That's it. And again, here you will have E, A, mu, D, E, A, mu. And that's it. A, mu, B. This is a relation between one forms. So if you want to make it more explicit, let's write the differentials E, A. Okay, let me change the index to rho here. Because remember, this form is something like that. And here we have, let me write again, the differential with the index mu, and then this will be some nu b. So you have this identity, and then you can drop dx mu everywhere because these are just one forms. The coefficients must be equal, and the complete relation then is as follows. This is completely general. We didn't make any assumption. This is just the relation between the Christoffel symbols in one basis and in the other basis. One case it's called Christoffel symbols, in the other case it's called spin connection, but there is no assumption, no metric compatibility, no torsionless assumption. This is completely general. Which tells you that gamma and omega are not independent. And we can define, so recall that we at some point defined a covariant derivative. Let me see where it was. Here, a covariant derivative with an object which was a K-form with an arbitrary number of indices, lower flat space indices. But those were flat space just because at that point we wanted to use flat space. But now that we know how to change basis to any basis, those indices can be anything, even space-time indices. And so we can extend this definition of covariant derivative to objects that are K-forms, have an arbitrary number of flat space indices, raised or lowered, and an arbitrary number of space-time indices, raised or lowered. Just by replacing here, when you have to deal with flat space indices, you will do it with a spin connection, and when you will have some lower or upper space-time indices, you will use the Christoffel one form built with the Christoffel symbols. So let's write this definition of the covariant derivative. We can define a covariant derivative of objects that have an arbitrary number of flat space indices and space-time indices. Just by replacing omega AB with gamma whatever, mu nu. For example, let me write the covariant derivative of this object, EA mu. Not as a form now, not as a vector, just the coefficients. This is a zero form, because it has no differential. It has one upper flat space index and one lower spacetime index. So what is this? This is the exterior derivative. Then how to deal with that, according to the definition we saw earlier, which we may want to check again. Upper indices are obtained by multiplying by omega to the left. Lower indices are obtained by multiplying by the corresponding omega, whatever it is, Christoffel symbols maybe in this case, to the right, and there is a minus 1 because now we are dealing with the zero form functions, so there is a minus 1. So what you get here is omega AB E B mu minus E A nu gamma nu. This is the covariant derivative of the field binding as the coefficients now, not the field binding as a form or as a vector. Now I want to show you that this is identically 0 with no assumption whatsoever. This is always 0. The covariant derivative of the field binding is always 0. It's not like the covariant derivative of the metric, which is 0 only if you have metric compatibility. This is always 0 because it is just the change of basis that we found earlier. It's just a rewriting of that. Always 0. So this is important. Why? Because you can work it out in terms of this is a one form because it's the covariant derivative of a 0 form, so it's a one form. So in particular, you can write del as dx mu d mu if you want to define the covariant derivative with indices. That's what you can do, and but the point is we want to show that whatever is to the right is 0. So what is to the right? We have dx rho partial rho e mu a. This is the first thing. Then you have dx rho omega rho a b e b mu. Okay, and then we have the last term, which is dx rho gamma rho mu nu e a nu. Again, this is an identity of one forms. We want to show that this is 0, so the coefficients must be 0, which is this plus that must be 0. So we want to show that this identity holds. And this is just a rewriting of the previous one. Now we check it, because the previous one was omega equal. We can just insert that, actually. Just insert that instead of omega here. Why not? Let's do that. We can do it that way. So we just replace this omega with that expression. So we have partial rho E A mu plus omega rho AB. Omega rho AB is omega mu, just change names to the indices. We have E A sigma gamma sigma rho nu E nu B, okay, plus this thing, E nu sigma partial rho E A sigma, something like that. Yes. Partial mu becomes partial rho. Okay, this is omega times EB mu. And then we have minus EA nu gamma nu rho mu. This is what we want to show that is identically 0. We repeat the first contribution, partial EA mu. Second contribution, you see you have this times that. There is a contraction of indices B, B, and that becomes quindi, so a delta mu nu. Delta mu nu means that you have a mu there. So you have a EA sigma gamma mu rho sigma and that's it. The other one is, we copy it, EA sigma partial rho E sigma A E B mu. Here there is a B. This is a B. Minus E A nu gamma nu rho mu. So you see that these two objects go away, and the other two also, because remember, you know that when you have this kind of derivative in between contractions of indices for matrices that are inverse of each other, you can integrate by parts, let's say, so you can write it that way. But then you have another contraction there which gives you a delta sigma mu. So you have correctly partial rho E mu A minus partial rho E mu A. Which means that the field line is always covariantly constant. Always. Just always. And there is no assumption there. And the reason is that it has two different indices, and so in the covariant derivative you have two different objects, and the the property of being covariantly constant is just the change of bases between those two. Now that we have defined this kind of covariant derivative with all sorts of indices, we can use it. And for example, we can consider the covariant derivative of the metric itself. What is it? It's an object with two lower indices, and so we have to multiply to the left with a minus sign because it's a zero form. We have something like that. Yes. So what is it? The exterior derivative minus g. So for the first index, you will have to do something like this. And for the second index, you will have to do something like that. That is the covariant derivative of g mu. In a basis, the usual one, we will have the covariant, this is the covariant derivative, so we can work out what we can call del rho g mu by decomposing this in components. So dx rho, this is partial rho g mu, minus g, okay, this is sigma nu, gamma sigma rho mu dx rho, minus dx rho g mu sigma gamma sigma rho nu. So you can write this, checking, comparing the components. And then you can repeat the argument we saw when we talked about metric compatibility. If this object is zero, then you have a unique expression. If this object is zero and the torsion is zero, so let's recall that we have both here. If the torsion is zero, which in this language means and the covariant derivative, then we have a unique expression for the Christoffel symbols in terms of the metric, which give the Levi-Civita connection. And when that happens, thanks to this relation, if gamma is a function of the metric, so gamma is a function of the field band, the spin connection will be a uniquely identified function of the field band, given by this formula. So if metric compatibility torsionless condition hold, there is one and only one expression for the spin connection. Then, which implies of E. So this is a function of G now, but G, let's recall that G is a function of E. And again, if these two conditions hold, then you have that everything, the connection is uniquely defined, and of course it has to be, if it is defined uniquely in one basis, it has to be defined in every other basis, because it's only a change of basis. Okay, let's stop 10 minutes.